Welcome back. This is week 3, and I believe this is video 5. And here's an example. Dr. Selmer's work. Don't want to pass it off as my own. We have this bar with a damper and a spring. And here's the length right here, and we know the mass of the bar. And we want to find the differential equation of motion. We want to find an expression for the critical damping constant, and then we want to find an expression for the natural frequency if underdamped. And chances are it would be underdamped, because why else would we ask for it? I don't know. Maybe because we just like asking for stuff. Maybe. I don't know. So in order to formulate this, because it isn't a standard thingy, we'll have to make an FBD and an IBD. And I'll do my best to draw it, although my hand is hovering over the board here, and so it's not as steady as it could be. Alright, so here is my support at ROY and ROX. And what do we have here? Let's see, we'll have gravity in the center, mg. We're going to have some spring forces. Well, no, we have a spring force. I guess I'm going to make this one in compression right here. And I'm going to use small angle assumptions. So the amount of deflection is going to be the length times the angle. And then we're also, so if we're moving over to the right, we're pulling on the damper. And that's going to be c times its velocity, which is L times theta dot, right? Because the c is a force that's proportional to velocity. And in terms of my position, this thing has rotated theta. And I will make it go counterclockwise with a moment of inertia about O times theta double dot. Now, one thing we know about I, O, is going to be, first off, 1/12 ml squared, but then also m times the distance from the center that it had to go, which is d over 2 squared. Oh, not d, L. L. Now, with the magic of math, you'll find out that that ends up being 1/3 ml squared. Right there, because you'll take 1/12 and you'll add in 1/4, and 1/4 plus 1/12 ends up being 1/3. So, there you go. So we'll take the sum of the moments about O is going to be equal to I, O. I was going to write alpha, but I'll just make it theta double dot. And we have a bunch of clockwise things. We have this is C, L, theta dot. All right, but then it's going to be that's going to be times L. Right, so and we have the small angle, so it's going to be CL squared theta dot. Because the CL theta dot, that was simply a force, but we need to be a moment. So the moment arm is going to be close to L because it's an approximation. We're going to have the same setup here, L squared theta, for the same reasoning. We will have it looks like minus mg, and that's going to be, I want to say that it's L over 2. Did I write that? Yeah, L over 2 times theta. Yeah, because that's going to be that. Yeah, that's going to be the distance of the arm. That makes sense. Okay, and then it's going to equal 1/3 m theta double dot. All right, so we can write the equation of motion now. where we got write it out. You know, we could what L half. Whoop, I forgot something. There you go. L squared theta double dot. Yes. 1/3 L squared theta double dot plus CL squared theta dot plus KL squared plus MGL over 2 theta equals 0. So this would be the differential equation of motion. Some people might prefer that we get rid of that 1/3, which is hard to see there. 1/3 as part of that. Let's continue on. I will I'll write this down now, but with dividing through by the 1/3 ML squared. So let's write that as a theta double dot plus this is going to be 3C over M, because I took a CL squared and I divided it by 3ML squared, so the L squared went away, and we have theta dot plus, and now here's going to be 3G, I swapped that one over, 2L, okay, plus 3K over M, theta equals 0. All right, so the easiest way, I think, to proceed with this, instead of trying to force it into a figure here, is, well, to first take a look at this portion right here, because this portion is going to be equal to 2 zeta, which is going to be equal to 3cm. This portion right here is going to be equal to, I think I'm correct in this, the natural frequency squared, which is 3g over 2l plus 3k over m. Right? Here's what I did. I go the substitute. So this is back to the where this stuff came from. Theta is equal to E theta t. Theta dot is equal to lambda. I said theta, but I meant lambda. Theta is equal to E lambda t. So then theta dot is equal to lambda E lambda t. And then theta double dot is equal to lambda squared E lambda t. We replace that in the stuff up above into this, which I might call the equation of motion. This is like, maybe it really, you know, it depends on what you want out of your equation of motion, but this could also be called the equation of motion. It's just divided through. Replace that in there, you get lambda squared plus 3c over m lambda plus 3g over 2l. Oops, almost closed that out. Plus 3k over m equals 0. And then find the roots. Find roots. And so the roots are going to be negative b plus or minus the square root of b squared minus 4ac, the whole thing over 2a, or minus 3 halves, that half comes from that 2a. A is equal to 1, so you don't need to worry about it. And that's plus or minus and b squared, which is 3 halves. No, the 3 halves comes from the thing on the bottom, right there, cm, right there you go. Squared minus 4ac, but the 2's that we're about to bring up from the bottom. Well, no, okay, because we had a 2 to bring up from the bottom, so the 4 goes away. We have 3g over 2l plus 3k over m. All right. So if you were going to have critical damping, right? So one of the things we're being asked is the expression for the critical damping, right here. Critical damping occurs when these two things equal each other. When they equal to 0 is when the damping is critical. So that means that so CC happens when 3 halves C over M. So what we're really doing is trying to find that what C is going to cause this is going to be 3G over 2L plus 3K over M square root of that, which is going to be C critical is going to be 2/3 M and square root of 3/2 G over L plus 3 times K over M. I think that's good enough. We could start trying to replace things like the K over M could be omega natural frequency squared, and then, but this is a good enough expression to find numerically. And then lastly, we want to find the expression for the damped natural frequency of this piece. So I would say that it's, and I think I can say this fairly, that this whole thing right here is going to be the damped natural frequency. I actually want to double check that. Now that I'm saying that, I think you should try to double check me. Because I'm feeling uncertain. But it should be right. I feel okay about it, but not 100% for sure that should be the damped natural frequency, but I think so. So we'll look in and check that out, double check on that. Let's see. How did we do? End show, discard. Yeah, 12 minutes, not so bad right there. Let's take a look and see while we're looking at it. I have a book. Let's see, let's go to our book. We should be using our book all the time anyway. And I don't know what those things are. Let me go to move you, oh, let's hide you. And scrolling and go to height. And we should be looking at our, is it damped? Yeah, viscously damped free vibration on 28. So boom, and so they're using S's instead of lambdas, and we're also using yeah, so right there, that's they're not using sines and cosines, but they're using the e raised to the a value, but they are interchangeable with very few exceptions right in there. Yeah, so I'm pretty confident that here you go. Here's cosine right there. So this is where they're describing they're using it. So this is the damped natural frequency right in there for us, and we can see, although they have the negative in there, which is interesting. I think ours has the opposite for negative. Yeah, okay. Well, I'm going to try to find this in another book written out the right way. I didn't do the algebra out, but I think you'll find that that's I wrote it correctly. 15 minutes.